You have written it? Wow.
Oh yes, I'm very prepared.
Okay.
Four past. I think we're gonna start. All right. I get the thumbs up from the director, so I'm gonna start. So today we have Ralf joining us. Ralf is a professor in theoretical astrophysics at Heidelberg University, and since last year he's also been a fellow at the Radcliffe Institute for Advanced Studies at Harvard. So we've been lucky enough, essentially, to convince him to venture north and join us at the CITA whilst he's in the same continent. If you read the archive, which I hope some of you do, then you have seen Ralph's name pop up probably a few times per week on topics related to modern and early universe star formation, interstellar medium, astrophysical turbulence, interstellar dust dynamics, and numerical software tools, just to name a few things. He's not only a prolific collaborator, of which I'm one of his collaborators, which is why everyone should chat to him today. He's also that guy who writes the reviews. So from the control of star formation by supersonic turbulence, of which Ralf has been a pioneer in developing the theory for, to the formation of first stars themselves, he's the guy that writes the reviews on these things. And on that note, I'll let Ralf educate us all on the nature of the first stars. Thank you very much, Ralf.
Now I have to go. All right. Thanks, James, for this very nice introduction. Thanks for having me. It has been a while that I have been in Toronto, so it's great to be here and that you have this fantastic weather just for me. So when I asked James what should I be talking about, he said you have this review and let's hear about the first stars. So I will essentially cover some of the topics that is covered in this review that I put together with Simon Glover a few years ago. And I want to start with some theoretical thoughts that we need to understand to piece together the formation pathways of the first stars. I also want to say a bit about the transition then from the very first stars that form, which are forming out of metal-free pristine gas, and because they enrich the universe with metals from their winds and supernova explosions, they change the course of subsequent star formation. So I will talk a bit about that. I would then digress into something that I find super cool, supermassive stars, which may be interesting for the community who wants to understand the occurrence of AGN activity at very high redshift. Because I will try to argue that the supermassive stars could be the seeds of the supermassive black hole we see at very high redshift. And I will then very briefly, if there is time, talk about constraints. So this will be a very theoretical talk, in the constraint business will be, I think, somewhat underrepresented. I think also owing to the highly speculative nature of this field. So essentially, I will base most of what I say about today about this on this review, and let's just get straight to it. Why is it cool to study the first stars? The general statement is they're cool because they were the first luminous objects that were visible to the human eye. So they were the so-called dark ages, as after the Big Bang and after inflation, matter and radiation decoupled, and so you see the cosmic microwave background and the cosmic microwave radiation, and as the universe expands, this slowly drifts through the wavelengths and eventually reaches the infrared and now is at sub-millimeter wavelengths, at microwaves. And so at that time the universe was completely dark and it was the first stars that light up the universe if there had been observers to see. they also are the starting points for galaxy formation and evolution. And I think this is a much more interesting way to motivate why it is interesting to look into the first stars. So, a bit about the physics. In principle, you need to have a number of very simple ingredients. So, as the universe expands, most of the matter is dominated by dark matter, and initially the baryons, so the gas out of which these first stars form, is along for the ride. As the dark matter decouples due to its own gravity, which happens for small objects first and then larger and larger ones, you need to ask the question, what do you need to really, have a runaway collapse of the baryons? So, unlike dark matter, the baryons are dissipative, and so two things need to happen. One is the James criterion, clearly its own self-gravity, needs to overwhelm the forces by gas pressure. So that is a criterion that we apply in star formation all over the place, everywhere. Gravity needs to dominate over all opposing forces, and clearly this needs to be the case for these first stars. And you can formulate it in many ways. Here I have formulated in terms of timescale, so if the gravitation timescale is smaller than the sound crossing time, gravity wins. But this is for isothermal gas, and the gas initially is hot, and you also need to look at the cooling properties of this gas. So the gas needs to be able to cool sufficiently rapidly to not heat up as it gets compressed. And so this is criterion that goes back to Martin Rees and Jerry Ostertag, and it needs to be that these two things need to happen at the same place, and then the baryons can go into a runaway collapse. Essentially, first they are along for the ride, then they flow into the dark matter potential, but eventually they run away and they could actually drag along the dark matter. This is then Blumenthal's adiabatic contraction. Then star formation sets in. So this has been, described in this cartoon in a very hand-wavy way. So what we want to put proper numbers. So the James criterion, the critical mass for these two happen scales with the sound speed to the third power and inversely with the density. So here in terms of the temperature. So the denser the gas, the more easily gravity wins, the hotter it is, the harder it is. We can translate that into cosmic expansion, so redshift, the content of baryons of the universe, of dark matter, and you can see that there are these formulae as function of redshift that tell me what is the critical mass for this collapse to occur. And this is a very simple picture. There are all kinds of processes that can complicate this thing. So we need to then ask, how can the gas cool? So at present days we have all the metals, CO rotational lines and all that stuff can provide sufficient cooling for the cold, I said it already, the dense and hence cold interstellar medium goes down to 10-20 Kelvin because we have all the metals. So there is nothing but hydrogen and helium and maybe a bit of lithium and beryllium after the Big Bang. So we need to ask, out of this simple chemical composition, what could be providing the cooling power? And it turns out the key question is, do we have molecular hydrogen, which has this forbidden transition, the quadrupole transition, and if you can excite it by collisions, it can radiate away these internal degrees of freedom, the internal excitation by issuing a photon, and if the photon escapes, you have efficiently cooled the gas. So in order to understand that stuff, you need to solve the chemistry network of primordial gas, which is simpler in many ways than the present day stuff. So there is a handful of reactions. As mentioned on the previous slide, the key aspect is how many free electrons do I have. That becomes important later on when we talk about, supermassive stars, because this will probably happen in regions that have been prevented to form lots of H2 by radiative interaction with neighboring bands. But these very simple chemical networks can be put into our models, and we do these first star formation calculations, solving such a network running alongside the magnetohydrogens. And so if we do that, we can simply ask what is then the temperature as function of the density. And what I plot here is a plot I made from data from Louis Prower. Essentially, it is a columns calculation in the cosmological context, following the behavior of the baryons in a smallish 10 to the 6 solar mass total dark matter array. And we start roughly here, and as the gas compresses, it forms more H2. Collisions tend to go quadratic with density, so you have quadratically more collisions and more cooling until we are somewhere down here. Gas sits around this phase, then slowly increases in density and temperature. It still is mostly atomic, so this is the fraction of molecular hydrogen. So mass fraction, so etc. is not at 1 but at 1/2. And eventually, if you are here, you can go to massive molecular hydrogen formation by the three-body process. So then you are quickly molecular. The contraction continues, and there is more stuff involved here. For instance, eventually you get so hot at around a few thousand Kelvin that you can collisionally also kill the molecular hydrogen molecule. And this has some latent heat involved because you have to break up the bond. And so there are features in this effective equation state. So we can look at details at this cooling behavior, and this is a typical cooling rates for different processes at the present day universe. So for solar metallicity, and you can see it's dominated by, let's say, the rotations and vibrations of carbon monoxide or fine structure line cooling of various atoms. If we go to the primordial gas, it all has to do with molecular hydrogen. And if you look closely, there is one thing that goes with HD, so the deuterated hydrogen molecule has a dipole moment, which you do not have in the symmetric molecule, so it only has forbidden transitions, but the HD has a dipole moment, and so it can provide, if you have enough of that stuff, efficient cooling and bring it down to relatively low temperatures, lower temperatures than with molecular hydrogen, so standard hydrogen cooling. And there are some stuff related to some of the other things. The most heating process is provided by simple PDV heat, so compressional heat, as the gas contracts. All right, so I've shown you the heating and cooling for primordial gas and before that for present day gas, but you can step through metallicity space. And so this has been done and has been pioneered by Kazuo Omokai. And so I'll show you what I call the Omokai plot, which gives you, again, as function of density, number density, the temperature for zero metallicity gas and present day gas. And you see kinks and features, and it has been argued, for instance, by Richard Larson, one of the key star formation people from Yale, that whenever you have a kink in the loitering phase, this you can read off, this is density temperature, exactly the same stuff that enters the genes analysis, so you can read off a critical mass. And it turns out in these loitering phases, this leads to an imprint in the mass distribution, in the INF, at least to first order. And so we can ask, what is then the critical mass that is associated with these various kinks and features? So let me just blow up this plot. And there's another feature that I think I need to address. So to the right, the material becomes optically thick to its own thermal radiation. So collisions excite internal degrees of freedom. They de-excite by emitting a thermal photon, if it is dust, or a photon in some wavelength, in some line, if it is other processes. And if the photon gets gobbled up by neighboring gas particles, then the energy cannot leave the system and you have no net cooling. So it needs to be optically thin to this cooling radiation, and at high densities this is not the case. So all the action takes place here, and this is just the adiabatic line modulo these modifications by latent heat and all that stuff.
Just a coincidence that that line is almost constant mass. That's how it becomes one line.
It's sort of
lucky, I guess.
It is a coincidence. There is the opacity limit for fragmentation that goes back to Lindenbell, Kriel, and others, and this is exactly this line, so to say. And it is roughly, so if you look at the Jeans lines, so these are lines of constant Jeans mass, and it's at the Jupiter mass level. And so, indeed, if you do very high resolution present-day collapse calculations, you start out with the first core, the first Larsen core in this mass range. And then it grows by accretion. And the same happens in the primordial case. This is 10 to the 2, and this is 1 solar mass. And you can see this is associated with kinks that have to do with different features taking over the cooling behavior. I'll come back to that when we talk about the transition from population 3 to population 2 star formation. So let me go to the primordial case. So I think one of the things to notice is it does not really have features and kinks. It is essentially isothermal over 10 orders of magnitude in density. So over 10 decades in density, temperature only rises by a factor of 2. So the effective adiabatic gamma would be 1.0 and a tiny bit. So it's almost isothermal, and it tells you fragmentation will probably form not in the turbulent phase, but in a disk phase. And so if you indeed put that into a super high resolution calculation of the first stars, I cannot resist and show you some of our own work, of Paul Clark's work when he was in Heidelberg. So what happens is material falls to the center because it comes with certain angular momentum, and accretion disk builds up. And it turns out the mass load onto the disk is larger than the mass transport by viscous and magneto-viscous transport. So the disk grows in mass, and eventually it becomes marginally gravitationally unstable. And it does what all gravitationally unstable disks will do. It first forms spiral arms. These spiral arms interact non-linearly, and you form a second object, and a third object, and a fourth object, and so on. The densities and the size scale is much larger and smaller in terms of size scale than what we expect for present-day protostellar planetary disks. So this happens within 100 years. And I show you a simulation that Thomas Greif did. And this is the density, this is 1 AU. And this is the temperature. This calculation resolves 100,000 kilometers. So it really resolves, there's no thin particle, nothing, you really resolve the first core. And the disk is super unstable. Most of the fragments merge, many are kicked out. And the really frightening aspect is this is 11.38 years.
Wow.
So, this is not even a percent of the total mass in the system. So this is the very first step. And the key question is, how does this continue? How does it continue in the presence of magnetic fields, in the presence of stellar feedback, in the presence of, let's say, dark matter annihilation providing heat, in the presence of additional stuff? And that, in a sense, is still the frontier, I would say, of this type of standard pathway of population 3 star formation, because no one has resolved the disk sufficiently enough over large enough time scales, including all really relevant physics. Simulations, I show you a few, either focus on this aspect, on that aspect, either geared to really resolve what's going on in the disk, or try to cover large timescales and then make assumptions about, formation of the stars, introduce thin particles, compromise on resolving the disk scale height, and so on and so forth. Nevertheless, you can ask this type and similar simulations about what is the expected mass spectrum. And we all know the mass spectrum for present-day stars follows essentially either a log normal followed by a power law or a multiple power law. It's crew power with Chabet, IMF. And the prediction here is instead it is something that is logarithmically flat. And this is from initial simulation of Paul Clark. This is Louis Proulx's thing, and you see it goes from the 0.01 solar mass to a few solar masses. This is from another one from our group. This is Hirano's work, which goes to much higher masses because he has much less resolution in the disk, so he does not have the fragmentation, but what he has is he has radiative feedback, which is not included here.
That was actually the question that came to mind with your simple atomic density curve, evolution curve. How much of a first generation galaxy follows that curve before a first star turd gas from it?
So these Omkai plot curves, let's see whether I can do that. So this is a one-dimensional simulation that follows the collapse. So it's a one-cell chemical evolution. The chemical network is much more elaborate than the one I showed you before, but its dynamics is much more simplified. So it is it is zero-dimensional. You can see it goes deeply down, so it is not informed in these early models about the cosmic microwave background. It should give you an orientation. So if we do it in 3D, the blue curve I've shown before roughly follows this, but not quite. This is intended as an indication of how it roughly looks like within a factor of 2. And this has no stellar feedback, so it's only compressional heat.
That was the question.
Yes. And okay, now we're back in this. So if I plot all of that, I think the agreement, most people in the community would say they have a logarithmically flat mass spectrum, which means, compared with the present-day IMF, it is top-heavy, because more mass is at the high mass field. And so the question is, where does it go? Does it really go to 1,000 solar masses? I have doubts, because these guys were not able to resolve the disk scale height. So the radiative feedback breaks out of the disk per definition. Whereas when we do that with high resolution, often the H2 region gets quenched in the disk and just depleted. So this is a picture that Eric Keto has put around for present-day star formation in the 2000s, so 20 years ago. So the question is, what happens to low masses? what happens at the high mass end, and then of course if you have stellar feedback, if you have magnetic fields, if you have dark matter annihilation, how does this picture change? So a quick digression into transition to pop 2 stars. So let me now go back to this effective equation of state and look at this part down here. And so there has been a debate in the community about what really causes the transition from primordial star formation to present-day star formation. Is it line cooling or is it dust cutting? And by accident, they overlap present days, but they split in the old days. So if you go to a metallicity of 10 to the minus 3, then they are separated by an order, 2 orders of magnitude in Jeans mass. And I think the very fact that we don't see much population 2 stars in the 100 solar mass range, there would be way too many black holes and all kinds of things. Most of them indicate low mass. It tells you that it must be the dust cooling that eventually dominates. But this has been dragging on for a while, and it was the occurrence of the Kafau star that kind of settled it, that most people would now say it's dust cooling that is more important. A little, to finish this digression, demonstration that if you have a kink in the equation of state, just like what Richard Larson has predicted now 40 years ago, 40 years, this guy was always right, amazing. This is really a visionary of star formation, that if you have a kink, this introduces a characteristic mass scale in the fragmentation process. And we modeled that. It was Katharina Janssen's work, and Richard was involved. And we indeed see that depending on where you place this kink, you can shift around the peak of the IMF. And there are much more elaborate ways to do that related to the turbulence and to the thermodynamics, and there is a recent annual reviews article by Patrick Hennebel and Chefs, I never can pronounce his name, who discussed the current state of affairs here.
Can you remind us where that kink comes from then?
Okay, the kink comes from this effect. The kink comes from dust cutting. So, dust is amazing. Dust acts largely as a thermostat. If you think of dust opacity in the radiation field of dust coupled to the thermal radiation, it goes with the fourth or fifth power of the temperature. So you can change the radiation field by a factor of 100,000 and you change the dust temperature only by a factor of 10 or even less, depending on how opacity you peak. So you can do a simulation where you allow for the coupling between the dust temperature and the gas temperature. So zero metallicity, 10 to the minus 6, minus 5, minus 4. And you see there's this kink evolving because then there are frequent enough collisions between dust and the gas particles such that the gas gives its excess thermal energy to the dust and the dust radiates. And so that is the key to cool gas at around 10 to the 4, 10 to the 5 particles per cubic centimeter in the present day. So dust is super important. And if we just look at how this influences the mass spectrum of the little fragments that form, we see flat here, developing a well-defined peak here. And this is not just us who found that. There is much more recent work with much higher resolution from John Omukai and Raphael Schneider is involved, which find a very similar aspect.
So you're saying the kink comes from that it's highly coupled at high density?
Yes.
And then the low density, the dust is decoupled, is that right?
Yes, here's decoupled. At the low,
That the kink is there?
so at this low density, I mean this is still high density, but this is a metallicity of 10 to the 4. If I bring it to present day metallicity, this would happen at 10 to the 5. between 10 to the 4 and 10 to the 5 and temperatures of 20 K. That was last point, 40 years ago.
Coincidence. To give one solar mass.
Lucky us. I would say, you know, if it is 10 solar mass, there will not be enough time to evolve.
No life.
So, it's probably a coincidence, but the IMF is relatively inert against environmental changes. And so, Bruce Elvegren has argued in 2008 paper, this is due to this is inert to lots of variations in the ambient range. And I think this is a correct point. All right, I need to speed up. So, there is more complication. I mentioned radiative feedback, magnetic field side meta-annihilation. There is also relative streaming instabilities that increase the level of turbulence in the star-forming gas. And so this will reduce the level of fragmentation, and this one will increase the level of fragmentation. And who wins? Who knows? So that is, I think, another frontier of really boiling down what is the IMF of the first mass. I cannot resist and intersect another intermezzo about the properties of the first mass. And I am talking about the standard population, 3 stars that have been entered the compact configuration. So the general story is, because there is no metals, there is less internal opacity in the star. The energy generation in the center is relatively similar to an equal mass present day star. So this is just the standard contrast diagram, and this is the present day stars, and this is primordial stars. This function of time, stellar lifetime distributed in chunks of 10%. So this is a giant phase, and this is the main sequence phase, so to say. And you can say most of these equal mass stars are roughly shifting just to higher temperatures, but roughly keep the same luminosity. So why are they more compact and hotter? Because there's less opacity, so the radiation can diffuse through the stellar interior more easily, and so the star can afford to be more compact, and hence it needs to be at higher temperature because it needs to radiate away roughly the same temperature. So remember that the luminosity goes r squared t to the 4th power. So this is just very simply the luminosity is proportional to r squared, that is the Boltzmann thing, and t to the 4th power. So if this is constant, the star shrinks because it has less internal resistance. The temperature needs to go up in order to keep the luminosity the same. So this is just the lifetime function of time. This is the luminosity, so we can easily have 10 to the 7 solar luminosities of the big guys. And these are not my data. I obtained them from the Geneva group who graciously provided them to me. This is the radius distribution, and I point out this is the radius in the compact configuration. I will argue soon there could be another pathway of primordial star formation that gives rise to radii that are a factor of 1,000 large. And recently we have also looked at the parsec tracks in the more or less system. So the stellar evolution models more or less agree with an factor of less than 2. You can ask then the question, what does it mean in terms of how to put Lang-Werner hydrogen ionizing, helium ionization, helium plus ionization. And the different curves are just the different metallicities. The dark guy is zero metallicity, and the red is solar metallicity. And this is the number of photons per baryon. So if you do a cosmological simulation and you just want to know how many UV photons do I get per proton, you can look at these plots. And they are also available in tabulated form. You can then also do that population average, and you can see the population 3 stars output much more ionizing photons, whatever you do. And that means if you have signs of a hard radiation field, let's say in James Webb observations, many people claim, oh, it must be population 3 cluster.
But is the critical thing that it's a log flat IMF?
No, the critical, that the key comes from these things are just hot and output movement. That is, I mean, the fact that it comes from going from log flat to Cooper is not so much. It's more dominated by different surface temperatures. But there's a caveat, and I took this from Thomas Bessie Jones. If you do a proper stellar atmosphere calculation, then you realize there are all kinds of features, and I may have overestimated the high energy, high frequency part of the spectrum. So this was simple black body approximation that essentially everyone uses in the community, but can lead to easily a factor of 2 deviations. And so this needs to be improved.
Just a quick question, the previous one, the high energy mass angle being zero metallicity mass spectrum, what determines that?
This one,
Yeah.
they stopped the calculation. They went to 500 solar masses, and this is
So there's no physical.
no, nothing at all. All right. So I will talk about in the remaining 5 minutes, right?
No, you have 10 minutes, you have
Okay, 10
15
minutes.
minutes.
Okay. So in the remaining minutes, let me digress from this standard pathway and ask the question: how can we go bigger, brighter, and more impressive? And for that, let's go back to the genes, right? So we have essentially 2 knobs to play with: the density and the temperature. So if we have a larger mass, for instance, like in atomic cooling halos, then we may get higher temperatures, higher fragmentation masses. Or, and this is something that the present-day star formation community has been playing with for ages, and I largely disagree with this approach, is if you have magnetic fields and if you assume the magnetic fluctuations are much smaller than the dynamical timescales, you can simply put that to the sound speed and have an effective temperature. So you're again playing with the temperature. So the pathway to getting more mass is cranking up the temperature, the effective temperature, however you do that. And so there is these atomic cooling halos where the idea is you have formed a first star forming event already in one halo, and you look at neighboring halos that have not yet formed a star, and so they are affected by the Lang-Werner or the ionizing radiation, and so they are not allowed to go into collapse because the temperature is much larger, or they are fully ionized and they don't have the H2 cooling chain. This is kind of Goldilocks problem. So 10 years ago, there was all kind of calculations, how far away, how much Lang-Werner, how much this and that. So you can achieve that, but it's somewhat contrived, which I think is good because you don't want this to happen too often. There's also the streaming velocity. So if you have a streaming velocity, a relative velocity between the baryons and the dark matter that comes from second order cosmological perturbation theory, then this can excite turbulence, velocity dispersion into the halo, and maybe this prevents gas from going into collapse. So this is something that, like, Anna Schauer looked at. And so she played both with a Line-Werner background and with different streaming velocity. So no Line-Werner background, increasing streaming velocity. So this is the standard scenario that most people look at. Intermediate, higher, even higher streaming velocity. This is the cosmological average, so 1 sigma streaming velocity, and cranking up this Line-Werner background in this function. And it turns out, the more you have, stronger your relative streaming, the less likely it is to go into collapse. And of course, the same is for the external irradiation. So this is the key quantity to look at, the H2 abundance. So hardly anything here, hardly anything here, lots of stuff down here. This immediately translates then in the critical mass for collapse as function of redshift. And I quickly go through this. You can update the formula I've shown you at the very beginning to take these factors into account. So if you don't have that in your cosmological simulation, you can bring it in by these kind of additional factors. So the problem is, however, if you do that, opposite happens of what you would expect. Because the gas is hotter, you have collisional ionization, you have free electrons that trigger runaway free electron. The free electrons trigger runaway H2 function. So you start out with more mass, but the gas is able to rapidly cool, and suddenly, instead of having 1 Jeans mass at these high temperatures, it has all cooled down to, I don't know, 500 solar masses and fragments like hell because it has many Jeans masses. So in these atomic cooling halos, you expect actually higher stellar densities and smaller fragment masses. So counterintuitive, but the numerical results kind of indicate that. I skipped that as well. And so this was the question of the mass reservoir, but there's also the question of the accretion rate. And so if you go back to the original Shu paper, everyone says m dot goes with the sound speed to the 3rd power, and these are just constants, and this is the factor of 0.93. But this factor is only 0.93 if you start with exactly 1 Jeans mass. If you cool down and suddenly you have thousands of Jeans masses, this factor is a very strong, strongly dependent on the Jeans mass. That is typically missed. It is in Frank Schu's appendix, and well, in the appendix of his paper. And we have looked at it in 2011. So that is something that needs to be taken into account. So you need the reservoir and you need high accretion rate. So the question is what happens with a star that is subjected to high accretion rates. And so this is from Lionel Henner's work, but it's the same Hosokawa and Wurzelbach. So having Russell diagram, and the only thing that changes is the accretion rate onto a tiny little blob of gas, going from thousands of solar mass up to 10 solar masses. And you see at around 0.10 to the minus 2 and 10 to the minus 1 solar masses per year accretion, the thing flips dramatically. These videos have to do, the guys have to stop the simulation, readjust the stellar atmosphere, and calculate again. So we had this problem, Hosokawa had this problem. So if you ever wonder where this comes from, this is a purely numerical artifact. But it goes away if you can manage to receive in your stellar evolution code these high accretion rates. Then suddenly your star is never relaxed. The entropy wave that is associated with the Kelvin-Helmholtz contraction phase never reaches the stellar surface. And this star is enormous. So as you know, this have lines of constant stellar radius. Solar radius 10, 100, 1,000, 10,000. These guys have 10,000 solar radius. And they have interesting internal stellar structures. So they have hydrogen burning, they have convective stuff. They really look like red supergiants. However, they are just super duper giants. They are much more massive. They are much larger, yet their surface temperatures are 3.5 to 4,000 Kelvin. They are very cold. They will not produce an appreciable number of UV photons. They are infrared bound. And eventually the red thing comes in. You can ask, if I just have the reservoir, what happens if I subject the star to just ongoing mass accretion rate? How long can it be stable? It can be stable up to a few 100,000 solar masses, and then the general relativistic instability kicks in. And when it kicks in depends now whether you use GENEC or MESA or PASEC.
That's for non-rotating, isn't it?
Rotation will not change stuff much. So Leon has a number of publications where he looks at, so this guy, where he looks at rotation. Rotation is tricky because if you assume some kind of internal magnetic fields, the question is how do they redistribute the angular momentum in the stellar interior? How efficient is that? And so on.
You say solid rotation will have
You can also have differential rotation, and then it would make it solid body rotation. But no one has done the calculation, so this depends on certain efficiency parameters that these guys need to assume and vary in order to see how the final result is. For further details, I have to refer you to Hammerle et al., who studied that stuff in great detail. He also has a good explanation for, so he essentially picked up where Chandrasekhar left and continued the analysis of the general relativistic instability. I had a very simple explanation for it, but it is completely wrong, so I will not give it here. But the star will become unstable and within its threefold timescale, so within hours, collapse to a black hole. There will be no supernova explosion. This thing will go to a 10 to the 6 solar mass black hole. And so I said, oh, this is great. We can, if we achieve this pathway, make the seeds for supermassive black holes. And you can ask, how do you get this accretion rates? And so in atomic cooling halos, you can easily get up to 10 solar masses per year. If you speak with Lucia Meyer in wet mergers, so gas-rich mergers at high redshift, he gets accretion rates of up to 1,000 solar masses towards the center. And then you cannot resolve things anymore. Then there's a gap of knowledge, and then our model comes in and asks if you subject it with 1,000 solar masses, what happens then with the same redshift? I've done this here. This is a summary plot that kind of summarizes all that stuff.
Is there an assumption when doing those models that the stellar luminosity can actually escape through the accretion stream?
Yes, that is the assumption. And that is not, these models are isolated stellar evolution calculations which have in addition the ability to predict what happens outside and how the material ends up at the stellar surface. Where it comes from is not subject to distance. That is the big question. And I need to, so, now I've given you two things that talk about exactly opposite things. So here I argued, if you have enough accretion rate in the large enough reservoir, you can make supermassive stars. I told you gas under these conditions will fluctuate. So how do we bring them together? And I should come to an end. The answer I would normally elaborate much further is that this material would form a cluster of stars, but this cluster of stars, because they are puffed up, they will collide. And so when we do these calculations, and I just show you one from our group, but there are many, many others. So there are 20 applications studying one aspect or the other of this. And many of them come to the conclusion there is collisional mass growth of one, maybe a binary object in the center that can gobble up easily 80% of the mass. So this could be a massive binary black hole and then influence subsequent galaxies. So I was very happy about this society and thought, oh, bingo, we have now a pathway to, this is not a direct collapse scenario because back to Wies and Martin Wies and Wegemann, but it goes through the detour of the star cluster and emerging within the star cluster. And the configuration is dense, the stars have radii of 1,000 plus solar masses, they're bound to have collisions. And we looked at all kinds of things. However, what we assumed is in most cases that if we have a collision, then we can easily add up the gas or at least lose a few percent by some crazy encounters. Now, Corinne Charbonnel tells me, if I have a 10 to the 4 solar mass of a supermassive star, and I place a 1 solar mass star, the sun on its surface and let it spiral in, it will unbind 30% of the envelopes. So the result of this more as gentle merger as you can get is that the resulting object will be 70% of the initial mass. So many of these collisions can actually lose mass rather than gain mass. And the conclusion is we need to do more stellar collision calculations to fully understand what it is. If this is a hyperbolic encounter, right, you can easily shed 70% of the mass. And how can you then form, if they all are limited by, I shed most of the mass, then they will never grow to a supermassive star. So that is, I think, something to ponder about, and I think that is an unsolved problem. How to constrain that? I think finding primordial stars in the high redshift universe is hard. I think one of the original science cases of James Webb was too optimistic at the time. More promising is galactic archaeology, constraining both the low mass and the high mass end of the IMF. And gravitational waves are, I think, an exciting new avenue. We talked about that just an hour ago, to also constrain the IMF. And with that, I'm 5 minutes over.
All right, questions? Maya.
Yeah, just a quick question about the stellar collisions. Is that, like you mentioned that these supermassive stars would be hard to see because they're cool and they don't allow UV radiation. But with the signatures of them, especially if they're losing mass, is that something actually bright enough to be observed?
We had of course, I could not resist the discussion about supermassive stars and the potential relation to the red dots James Webb sees at high redshift. And my proposition was maybe we see these supermassive stars because they would be red supergiants. But you showed a paper where there was no dust prepared. And so I think that is hard to reconcile with this type of scenario. So I think there is just more work that needs to be done and studied that in a more realistic environment. So it could indeed be that if you have this encounter, it sheds the outer layers of the star, you will then suddenly see a much hotter photosphere and it could light up in UV. It could change the entire thing. But this is speculation. No one has done any of these models. Corinne has also not published this, to my knowledge. So I think that is stuff that needs to be done. So, you know, I find it much more interesting to not claim, oh, we have solved all the puzzles of the universe. I think to point out what is the current frontier and what is it really that where we need to make more models, more observations, I think is much more interesting. And maybe some of you.
Maybe just one more question, then we'll go upstairs and have a chat.
Thanks, Ralf. Great talk. You covered a lot of topics. So you reminded me of Richard Russell's theory of the IMF and the low mass objects. So I was wondering, like, you know that the alternative, or one alternative explanation for low mass objects in the present day are outflows at every time, so that mass, perhaps ejections also, so two mechanisms. Do you see, well, if you think that has a role in the present day, do you see a kind of transition as you go to high redshift or zero metallicity, where those have less or no effect, and that maybe can explain the differences in the IMF?
So, I'm not a full-fledged subscriber of the X-Win model limiting accretion onto a low mass object. I'm also not a full subscriber of the one-to-one relation between the core mass function on the IMF. I think we see, at least at the high mass end, an increasing deviation from it. From the IMA IMF, our own IMA Gall survey, and now we see evidence for deviations also in the large majority count in 32 hours. So having said that, I think even at present days the relation is much less clear than maybe previously thought. Clearly, magnetic fields will play a role, as we discussed also in the primordial case. As I would argue, and I guess you would agree from our discussion, the magnetic fields will be amplified to saturation level in the formation of the first stars. I would argue even very early, because of the small scale dynamo, you would argue as soon as you have a disk, then the alpha omega takes over and beats it up even further and makes it more coherent. This would come along with outflows. There is early work by Machida, and there is your work, and I think that is something that needs to be investigated further. I think we also need to ask ourselves about the importance of non-ideal NHD effects in this context. That Patrick Enebel, for instance, argues is very important in the present day context, and I think it has been neglected more than NHD itself in the primordial case. So I think that is a lot to be looked at in the context of POP3 stars. And this is certainly one of the frontiers, and so I'm glad that you are approaching that from your side.
Okay, let's thank Ralf one more time. We'll go upstairs for discussion and coffee and maybe cookies.
So no questions from the
Oh, did you exit out of the Did you exit out?
I'm wondering that you allow for questions, because the speakers
True, and it looks like yeah, I could have asked. But yeah, I should have asked. No questions in the chat.
Aye.